Hello guys, welcome to this video. We are looking at a particular past question that keeps repeating itself on and on and on. Now even if this particular question might not be a past question to you wherever you're watching from, I want you to learn how to solve it because it is very important. So I'm gonna take my time and let's try and flow together. The video might be long, but just make sure that you follow me at each step. And the most important thing is that at the end of the day, you understand every move that I make and you can independently replicate the solution to this problem by yourself. So let's dive in properly. So we have two particular questions under this particular past question. The first one is you need to enumerate the 4 steps to be employed in the use of Laplace transform to solve ordinary constant coefficient differential equation. Then secondly, we need to use Laplace transform to solve the engineering system represented by the following set of ODE. So amazing, we have to solve a system of equations with Laplace transform, not just a system of equations, but a system of ordinary differential equations. So let's start with the first problem, which is a piece of cake simile. So let's go to the solutions. Okay. So for the first one, we are going to list out 4 steps that are usually employed in the use of Laplace transform to solving ordinary, as you can see, constant coefficient differential equation. So number 1 is you need to take the Laplace transform of both sides of the differential equation. Okay, now in step 2, after taking the Laplace transform of both sides of the differential equation, you need to apply the initial conditions. Okay, you need to apply the initial conditions in step 2, and step 3 tells us we need to solve for the transfer function, okay, in terms of the variable s. Okay, so for instance, we want to obtain y of s or x of s as the case may be, or f of s as the case may be. We want to solve for this particular function. So this particular function, capital letter y of s or x of s or f of s, in Laplace transform we call it transfer function, particularly in differential equation or system of differential equations, we call it the transfer function. And finally, you have to obtain the inverse Laplace transform of the transfer function to obtain the particular solution to the differential equation. So after you find the transfer function, it's going to be an expression in terms of s. Then the last step is you need to find the inverse Laplace transform of that expression in terms of s, which is going to be a fraction. So when you find the inverse Laplace transform of that fraction, then you now have to regard the answer that you get as your particular solution. So I'm using particular solution because particular solution stems from cases when you have applied initial conditions. It's not going to be a general solution. General solution is when we have not yet applied initial conditions, but particular solutions is when you have applied an initial condition, then you get a particular solution. So these are the 4 steps that you take when you're using Laplace transform to solve for ordinary constant coefficient differential equation. Now, in the B part of the question, we are going to be solving this system of equation over here. So let's solve for this system of equation and see what we're gonna get. So I'm gonna copy it and I'm going to paste it over here for step B. Okay, so the B part of the question is we want to solve this system of equations. The initial condition is x of 0 is 0 and y of 0 is unity 1. So let's solve this system of equation with Laplace transform. So follow me, it's going to be interesting and I believe you are going to love it. So the first thing we need to do when we are solving for this system of equation is to what? Take the Laplace transform of both sides. So taking the Laplace transform of both sides, this is what we are going to get. So for 2x bar plus y equal to cos t, we have the Laplace transform of 2x bar plus y is equal to Laplace transform of cos t. So let's see what we're going to get. So applying the principle of linearity, we want to find the Laplace transform of 2x bar plus the Laplace transform of y is equal to the Laplace transform of cos t. So if you resolve this, you're going to get 2. Now 2 is a constant, so it won't be affected. Then what is the Laplace transform of an x prime? So if you've been following me carefully, I have created a video where I showed us the Laplace transform of derivatives. X prime is the first derivative, so I'm going to have an s, then capital letter x of s, then minus x of 0. Okay, so this is initial condition, then plus Laplace transform of y is a y of s. Then the Laplace transform of cos t is going to give me s all over s squared plus 1. Is that okay? 1 is because the angular frequency here is the hidden coefficient 1. So if you solve this particular stuff and you apply the initial conditions, that's the second step. You have your x of 0 as 0, okay, from the question. So if x of 0 is 0, we can now go ahead and substitute it into this equation. So I'll now have 2x of 2s x of s minus 0, then plus y of s equal to s all over s squared plus 1. So at last I have 2s x of s and plus y of s is equal to s all over s squared plus 1. So I'll call this equation 1. Okay, so we have succeeded in getting this particular term for this first system. Okay, we have succeeded in getting equation 1 for the first system. Now for this second one, y prime minus 2x equal to sine t. So for y prime minus 2x equal to sine t, when we take the Laplace transform of both sides, we'll have this Laplace transform of sine t. Is that okay? So once we have it like this, what are we going to do next? So this is what we are going to do next. As usual, the Laplace transform is linear, so you can take the Laplace of this and the Laplace of this at once. This is a y prime, so the Laplace transform of y prime is going to give you s, capital letter y of s, and minus y of 0. Is that okay? That's for the Laplace transform of y prime. Then minus 2, then the Laplace transform of x is capital letter x of s, and is equal to the Laplace transform of sine t for an angular frequency of 1 is going to give you 1 all over s squared plus 1. Is that okay? So we apply the initial condition y of 0 equal to 1, and we are going to get s y of s minus 1 minus 2x of s is equal to 1 all over s squared plus 1. So when we keep solving this, guess what we are going to get? Okay, that's right. So what we are going to get is we're going to get s y of s, then minus 2x of s is equal to 1 all over s squared plus 1 and plus 1 over here. So s y of s minus 2x of s is equal to 1 plus s squared plus 1 all over s squared plus 1, and this gives me a 2 plus s squared all over s squared plus 1. Is that okay? So if you put it all together, you have s y of s minus what? 2x of s is equal to, what we have is, we have 2 plus s squared all over s squared plus 1. So I can call this equation 2. Is that okay? So we have gotten equation 1 and equation 2, and now we are going to solve them simultaneously because we want to get the value for the transfer function of x and the value for the transfer function of y. So this is how we are going to go about that. So we are going to solve it simultaneously. So this is what we are given. So given from equation 1 and 2, we have in the first case 2s x of s plus y of s, 2s x of s plus y of s is equal to s over s squared plus 1. I hope I got that right. Okay, I think I did. Then in the second case, we have, I can just rearrange it so that I'll place s on x under x and y under y. So I'll have negative 2x of s, then I now have plus s y of s is equal to 2 plus s squared all over s squared plus 1. So this is equation 1 and this is equation 2. Is that okay? So we are going to solve this particular system of equations simultaneously and see what we are going to get from the answer. So let me copy it and place it on somewhere else. So follow me. Okay guys, this is where we stopped and we are about to resolve this system of equations. So to resolve this system of equations, I want to remind you that you don't have to use elimination or substitution method because it's going to be very difficult and prone to lots of errors. So why don't we use another technique? That's the Cramer's rule. So if I want to find my x, for instance, my x of s, I can call it a delta x over delta naught. And similarly, my y of s, I can call it a delta y over delta naught. Okay, so this method will save you a lot of stress and a lot of, potential mistakes. Okay, so this is how easy finding x of s is. So take a breath and let's dive in. Now to find what delta x means, x of s is delta x. So delta x is a determinant that is formed from playing with the coefficients in this particular equation. Now to get delta x, okay, to get delta x, how do you get delta x? Now observe the coefficient of x of s in this particular equation. I have 2 up here and I have 2s up here and negative 2 down here. So what will happen is that I'm going to replace these coefficients with these terms here. Is that okay? So you replace it with the terms on the other side of the equality. So what you're going to get is s over s squared plus 1. Then you now have 2 plus s squared over s squared plus 1. Okay, so you've replaced it. Then the other part of the determinant will be formed from the coefficients of y of s, that is 1 and s. Is that okay? 1 and s. So this gives you your delta x. Now to get delta naught is just the coefficient of what? X and y in both equations. So I have 2, 1 minus 2 and s. So sorry, 2s1 minus 2 and s. So I have 2s1 minus 2 then s. Is that okay? 2s1 minus 2 then s. So this is how we have obtained the determinant matrix. Then we can now finally solve for this particular determinant. So this times this is going to give you an s square all over s square plus 1, then minus this times this is going to give you 2 plus s square all over s square plus 1. So divided by what? This times this is going to give me a 2s square, and this times this is going to give me plus 2. Okay, I hope you can see that. Okay, it's a plus because this times this first, then minus this times this is already negative, so the negative is interfering with that minus to give you this plus sign over here. So when we simplify, we're going to get s square minus 2 then minus s square all over s square plus 1, then everything divided by 2 brackets s square plus 1. Okay, as you can see, I factored out 2 from this side. So the numerator is already giving me this is still the same thing as negative 2 all over s square plus 1, then divided by s square plus 1 is a 2 here. So these 2 can cancel out these 2 up here. So what I am left with is the x of s is equal to minus 1 all over s square plus 1 divided by s square plus 1, and this evaluates to minus 1 all over s square plus 1 all squared. Okay, so this is equation 3. Now you have gotten your x of s, so you're going to keep it somewhere because it's going to be useful very soon. So we've gotten our x of s, and we are going to keep it somewhere because we are going to use it to find our small letter x of t. So before we find small letter x of t, I don't want to miss the fun. Let's find y of s. Y of s is delta y all over delta naught. So let's find delta y and delta naught together. Delta naught has already been found. Okay, we can just use delta naught from the previous equation. So the matrix for delta naught is 2s1 negative 2 and s. So what is the problem now is to find delta y. So I want you to pause this video and see if you can find delta y. Okay, so delta y, what is delta y going to be? Okay, so I guess you must have paused the video, so let me show you. I hope you got it correctly. So to find delta y is just all about replacing you need to replace this coefficients of y in this side with the terms in this equality. Okay, so the position of x will stay as it is, but y, the coefficient, will be replaced by this and this. Okay, in the respective equations. In equation 1 you replace 1 with this, and in equation 2 you replace s with this. So to get my delta y, this is how it's going to be. It's going to be like this. So for x, what are the coefficients? I have 2s and negative 2. So you will have 2s and negative 2. Then for y, instead of me to have 1 and s, I'm going to have s over s squared plus 1. Okay, and what? 2 plus s squared over s squared plus 1. So I'm gonna have s over s square plus 1, then 2 plus s square over s square plus 1. Okay, at this point we are now good to what? Start evaluating what the determinants will be. So y of s is now going to be, so from this particular one, if you do this times this, you're going to have 2s into 2 plus s square and all over s square plus 1. Okay, so you've done this times this, then minus this times this is going to give you a plus because of this, so you have plus 2s all over s square plus 1. Okay, so you've done the numerator part, then the denominator is still going to be this, because when you evaluate these determinants you get this. So I have 2s square plus 2, so I have what? 2s square plus 2. So let's be careful while we keep on solving. Opening this bracket, you're going to have 2s. Okay, 2s is common, but let me just show you how I'm going to do it. If it's by me, I'll have 2s, then 2s squared, then you now have plus 2s all over s squared plus 1. Everything here divided by 2s squared plus 2. Is that okay? So you have your y of s to be, you can now factor out what? 2s. So you have 2s into 2 plus s squared, then plus 1. I hope that is correct. When you factor out 2s, this is what you get, and you now have s squared plus 1, then all over 2 into s squared plus 1. So these 2 can cancel out this 2, then we'll now be left with what? 3 plus s squared, that's 2 plus 1, all over s squared plus 1, then divided by s squared plus 1. And if you do this very carefully, you will have your y of s to be 3. Okay, there is an s outside. Okay, I missed that. Thank you for that observation. So you have an s outside. Let's not miss it. S brackets, this plus this is a 3, then s squared all over this. So you now have s brackets 3 plus s squared all over s squared plus 1 all squared. Okay, this guy comes over to multiply this. Now you get your answer. Okay, so this is my y of s, and this is equation 4. So what have we gotten so far? So what we've gotten so far, okay, we got our x of s to be minus 1 all over s squared plus 1 all squared, and our y of s to be what? We have s into 3 plus s squared all over s squared plus 1 all squared. So at this point we are almost done. We can now go ahead and find the inverse Laplace transform of equation 3 and equation 4, so that we can get the x of t and the what? Y of t, which we will call the solutions to our system of equations. So consider x of s equal to minus 1 all over s squared plus 1 all squared. Okay, so this is the first one we are going to consider. So we'll say x of t is the inverse Laplace transform of x of s, which is the inverse Laplace transform of minus 1 all over s squared plus 1 all squared. Okay, which is still the same thing as minus Laplace inverse of 1 all over s squared plus 1 all squared, like this. Now, to solve this kind of problem in an exam scenario will be very tough. So what I did was, in the video just before this one, I went extra miles to derive a general expression for this particular kind of Laplace inverse. So I feel in the exam scenario you won't be out of place to just dive straight into the use of formula. So this is how I'm gonna do it if I were you. And if you're interested in knowing how I derive this formula that I'm about to show you now, you can watch the video just before this one. But in the exam, please do not derive the formula, just use the formula. Is that okay? Use the formula in exam scenarios. So, okay, we have seen by convolution theory that the inverse Laplace transform of a general form like this, s squared plus omega squared all squared, translates to 1 all over 2 omega squared, and you now have a sine omega t all over omega and minus t cos omega t. Okay, so we have seen by convolution theory. So you see, I already memorized it. So if an old man like me can memorize this, then a young person like you, certainly learning this thing from any time in the future, you should be able to memorize this too. And if you're interested in learning how it was derived, I derived it in the video just before this one. You can check my playlist so that you can see how to derive it. So please don't forget to like and subscribe, please, as you're watching. I need your likes, it means a lot, so that the video can fly to everywhere in the world. Now, at this point, we can now use this to resolve our what? X of t, being minus Laplace inverse of 1 all over s squared plus 1 all squared. So if you compare it very carefully, you will discover that omega in this case is 1. So for our omega equal to 1, our Laplace inverse is going to be minus, then the Laplace inverse of this will be compared to the Laplace inverse of this. We are just going to use this formula directly. So you have minus, then I have 1 all over 2, then omega is 1 squared, and you now have sine 1 times t is t all over 1, then minus t cos 1 times t is another t, and you now have it like this. Then finally we will now have our x of t is going to be what? Negative 1 all over 2 into sine t minus t cos t. Someone else can say that his answer is the same thing as 1 all over 2 into t cos t minus sine t. That is the value of your x. And how did this come about? When you use this minus sign to open the bracket, the minus sign will change the positions of this particular term. Of course, I decided to arrange a positive t cos t before a negative sine t that would have occurred when you open the bracket with the negative sign. So this is the value of the x part of this system of equation. X of t is half t cos t minus sine t. So let's go on and find out what y is going to be. So to do that, I'm going to copy out y of s, and we are going to solve it later. Stay with me. Okay guys, we are now at almost the pinnacle of our work here, and we are going to find y of t as the inverse Laplace transform of what? Y of s, which corresponds to the inverse Laplace transform of s into s squared plus 3. It's still the same thing as 3 plus x squared, and you now have x squared plus 1 all squared. Okay, so how do we go about finding the inverse of this function? So I want you to pay attention as I solve this. So this function is not so easy unless you split it into different units by your knowledge of partial fraction. So consider we have s into s squared plus 3 all over what? S squared plus 1 all squared. Now by partial fraction, this is going to be an as plus b all over s squared plus 1 like this, and plus a cs plus d all over s squared plus 1 all squared. Okay, so we remember when we have linear factors or quadratic factors that are repeated, it will follow this pattern in representing it in the equivalent partial fractions. So if we multiply both sides, by s squared plus 1 all squared, we're going to get s into s squared plus 3 is equal to, then this times this term is going to cancel out 1 and you'll be left with only 1. So you have as plus b on s squared plus 1. Then this times this will cancel out and you just be left with what? Cs plus d. Now I'm going to show you a swift and fast approach to solve these partial fractions. I can see an s multiplying in a bracket. This is always an advantage to me because I can simply put s to be 0. So in the first instance, when I put s to be 0, the whole left hand side becomes 0 is equal to, then this becomes 0, then you just have b, okay, then dot from this bracket, then s squared being 0, 0 plus 1 is 1, and you now have cs means c times 0, and you just have d. So in other words, b plus d is equal to 0, therefore b is equal to negative d, or d is equal to negative b. Okay, so we're going to keep this somewhere. So the next thing that you want to do is perhaps you want to compare terms in s cube. So let's compare terms in s cube, the contributions from the left hand side and the contributions from the right hand side. From the left hand side, we can observe that if we open this bracket, I'm not going to open the bracket, I just want you to observe. You need to train your eyes to observe, and this method of observation, I call it leap of faith. So yeah, I introduced it earlier in one of in the first problems on Laplace transform. That's the Laplace transform video number 1 for this particular series. If you want to see more about leap of faith, you can check it out. So we're going to use leap of faith to compare coefficients. Okay, leap of faith because you're not opening the brackets, you're just using your eyes to observe. So this is what I call it. I don't know what other persons or mathematicians call it. Now we're going to compare terms in x cube. When I open this bracket, I'm going to get my first s cube, and it's going to have a coefficient of 1. Okay, if you look at it very carefully, so 1 is equal to, now when I open this bracket, the only contribution of s cube is going to have the coefficient a, so nothing else, therefore a is equal to 1. So that was quite fast and easy. So we've compared terms in s cube. Now another thing I can do again is I want to compare terms in s squared, or let me compare terms in, is it necessary to compare terms in s squared? Do you think it's necessary? Let me just jump intentionally. Let me compare terms in s. So if I compare terms in s, from the left hand side, you will observe that when we expand the bracket, we're going to have a 3s. So the coefficient on the left hand side is going to be 3 for s. Now if we expand on the right hand side, the terms in s that we're going to be getting is we're going to get an as. Okay, as is one contribution. Of course you can see as times 1 is as, therefore we have 1 from here, then we now have cs. So from the left hand side you have a plus c. Now a is already 1, so if you put a equal to 1 in this equation, you have 3 is equal to 1 plus c, implies that c must be 2. So we've gotten the value of a and c. So finally let's go for another one. Okay, so if you compare terms in constant, I like using k for constant. So terms, or the constant terms, okay, when you compare the constant terms from the left hand side, I can't see any constant term because when I open, I'll have s cubed plus 3s. That means the coefficient of the constant term is 0. So from the left hand side, we have 0 as the constant term. Then in the right hand side, I can see only one constant term. Okay, I can see 2 constant term actually. So you will have as squared plus bs, as cubed, and you now have a b, and you now have what? Your c, you now have your d. Is that okay? So this leaves us with what? Very good. So you just be left with, for the constant term, 0 is equal to, you have b times 1 then plus d. b plus d. So this is our constant term, and this still leads us to that equation that b is equal to minus d. Is that okay? So the problem is, how do we now find the value of b and d? How do we find the value of b and d? Okay, this is where that one that we jumped become handy. Maybe if we can use it very well, we might be able to find an option for terms in s square. So terms in s square. So for terms in s square, what you're just going to do is observe from the left hand side over here. You can't see any term in s square, because if you open the brackets, s times s square is s cubed, and you have 3s. So s squared 2 must be 0. So in the left hand side, so 0 is equal to, so let's find out all the contributions of s squared in the right hand side. So as times s cubed is an as cube. Okay, then you now have as, you have cs, ds. The only contribution of s squared in the right hand side, if we open these brackets properly, will be b, if you check it very well. So the only contribution will be b. Okay, so b is equal to 0, therefore d is equal to minus b is equal to minus 0 is equal to 0. So b and d are both 0, therefore a is 1 and c is 2. So we found a, b, c, d to be 1, 0, 2, 0 respectively. So we can now round up these particular partial fractions in this way, that our partial fraction s into s squared plus 3 all over s squared plus 1 all squared can also be written like this. Our a is 1, then our b is 0. 1 times s is s, so I'll have an s over s squared plus 1. Then you now have a plus. Then what do you now have for your cs? Your c is 2. 2 times s is what? 2s. Then d is 0. So you just have 2s all over what? S plus 1 squared. So you have what? 2s over s squared plus 1 all squared. So this is our y of s. So y of s is given to us in this particular form as what? S over s squared plus 1, then plus 2s over s squared plus 1 all squared. So to find y of t, you take the inverse Laplace transform of your y of s, which is s over s squared plus 1 and plus 2s over s squared plus 1 all squared. Now, to get the inverse Laplace transform of this one, you discover is easy. Let me just apply linearity. You have inverse Laplace of s over s squared plus 1 and plus if you apply linearity here, you get 2 Laplace inverse of s over s squared plus 1 all squared. Now, the main issue is on this particular one over here. Okay, and to resolve it, we still have to borrow knowledge from convolution. So we also saw by convolution that the inverse Laplace of s over s squared plus omega squared all squared is given to me as this function. You now have t sine omega t all over 2 omega. Okay, so we were able to prove this in the last video, and if you're interested in knowing how we got this particular stuff, you can check out the last video. The reason why we are using convolution here is because in exam scenarios, trust me, if you want to evaluate this, it's going to take a lot of time. So you need to memorize this particular expression so that it can be handy for you. So to round it up now, we are going to apply this formula to this part over here, and we can see that our omega in this case is going to be 1. So you already know the answer to this one. Please, if you don't know the answer to this one, I am so going to encourage you to watch the series of videos on Laplace. Watch the one of the Laplace toolkit, yes, your Laplace handbook, where I discuss the Laplace of almost all the functions that you need to know, okay, for this course. Then y of t in this case is the inverse Laplace of s over s squared plus 1, and angular frequency of 1 belongs to the function cos t, cos 1t, then plus 2. Then let's apply the inverse Laplace to this case over here. So with an angular frequency of 1, I'm going to have t sine, then here is 1 times t, which is t, all over 2 times 1, which is what? 2. So 2 cancels out 2, and at the end of the day, my y of t is a cos t plus t sine t. Is that okay? Cos t plus t sine t. So finally, x of t, if you can remember, let me try to see if I can remember. X of t is 1 over 2. We now have a t cos t minus sine t. Then my y of t is actually a cos t then plus t sine t, and this is where you draw the pen. So I guess we are done. I hope the video was interesting. I hope you learned how to resolve the biggest enigmas, the biggest past question that have always stood out amongst past questions in Laplace transform for years. So if you are not seeing this as a past question, I hope you actually still learned how to get the answer to this particular question. So we are done, and we are done for good, and I believe you are able to apply these principles to, you know, resolving any problem such as a system of equations that you may be given. So thank you for watching this video. Meditate on it, try to replicate it by yourself. Please like the video, please share to your friends, and hit the notification button to stay updated. And be reminded that if you have any Laplace transform problem at all that you would want me to look at, you could always send me a message or drop a comment, leave a comment, and I'll be pleased to attend to your query. Okay, so till the next video, stay blessed. Bye.